Welcome back. My name is Danny. So in today's lesson, we're gonna talk about a little bit deep dive into the switching. So that we can see some of the theory behind the thing. So let's get started. So first, we want to talk about a overlay and underlay. So just emphasize and also told you about overlay and underlay. For example, we talk about how tunnel works and how to create your segment on top of that tunnel. So those are just here, just give you a recap for overlay and underlay, because you know NSX is a type of implementation of the SDN. So when in terms of the SDN, we just we have overlay, which is VX line encapsulation or data plane encapsulation, and also have some of the overlay, which is segment. So for NSX 4.0, we have a Geneva tunnel, which is a variant of the VX line. So we just take a close look at this, the Geneva tunnel. Geneva tunnel is a TCP encapsulated TCP protocol, and over the 6081 TCP port, UDP port. So it just kind of like a MAC over UDP. Because the Geneva is kind of like a proprietary protocol invented by VMware. Just you can think of that 95% of the Geneva is the same with VX line standard. So VMware just only add some of the TLV, for example, here, and also add some of the specific proprietary and specific fields on this VX line encapsulation, so make it more flexible for example, to carry in other fields and for NSX to work well. So when we look at the header format, Geneva of Geneva, we can see here is there is a VNI, 24-bit VNI. VNI kind of like VX line VLAN ID. So everybody, I think everybody knew that VLAN ID is 0 to 6,096. So the maximum they are 4,000 VLANs you can use, but for VNI there's a 24-bit of this VNI, so they are much more than the VLAN ID. So you can use thoroughly or just use a lot of VNI to segment or kind of like separate your application to different VNIs, separate your your subnet or segment to different VNIs, so you can make it more manageable. So, like I said, Geneva UDP-based encapsulation is pretty similar to Mixline. You just need to remember some of the keywords, for example, TRV. So just add some the specific TRVs onto the Geneva protocol. So it's pretty neat for NSX to carry some of the specific fields. So let's talk about some of the three tables here, under the hood. So for example, when you look at the layer 2 switching, traditional layer 2 switching, generally there are a lot of multiple port interfaces or multiple ports on this physical switches, for example, 24 or 48 ports. No matter what speed they are, 10 or 100 or 1000 giga-E or 10 giga-E or 100 giga-E, it doesn't matter. The theory behind the thing is the same. So when the packet comes in, what is layer 2 frame, I should say, to be accurate, layer 2 frame, because when you look at this, how the switches work, they work at layer 2. So they help transmit layer 2 frame from the port to another port, and vice versa. So it's just when the layer 2 frames comes in to a specific port, they just started to build some of the very necessary tables. For example, MAC table. So you can type in show MAC table on Catalyst or Cisco Catalyst switch to show the MAC, a certain MAC, and map to a specific interface. That means that the switcher system know where this MAC, or this MAC means that the NIC, every NIC has a MAC where the MAC is, where the NIC is, so they can just intelligently transform and transmit the packet layer 2 frame to the destination from the source port to the destination port. They can also have other tables for forwarding, to do some performance forwarding, things like that. But general theory for the layer 2 switching is a MAC table, and also have some of the important table. So here, back to NSX as a layer 2 switching, we're going to talk about 3 tables. So which is the TEP tables and app table and MAC table. So to see how NSX works. So for example, let's say there's a new VM comes in and powered on and on the ESSI-8, which is a -TN. we talk about that. We have 3 TMs here. So when the new VM power down or just started, so it just NSX just cares about which NIC or what segment it is attached to. So for example, there's a green segment with the VNI number 5000. So this VM is attached to the VNI 5000 segment, which is a color green. So that means we have to create some of the table for the whole system to run. For example, here is how to create the TEP table, because we have a VM and whose VNI is 5000 and ESSI A TEP IP is 10, 20, 10, 11. That means there's a map and there's a mapping between the VNI, this VM, the VNI, and the place this VM is located in. So here's a ESSI-A TEP IP. So the same thing happened on the third one, on the second one, and the third one. Even if it's KVM, but NSX 4.0 doesn't support KVM, so it just pretend to be ESSI-3 or -C, ESSI-C. So we have A, B, C ESSI hosts. So that means there's a 3 VM and also 3 tables here. 3. So later on is we have to these 3 discrete or distributed information will go up to the CCP, centralized controller plane. So to the controller will collect all of the tab table and distribute it or hand out to every distributed nodes or every distributed TM transport node. So to make sure that at the end of the day, so every transport node has its same scenario of this table. So everybody just see the same thing. So here we have VNI 5000 and here's the 3 ESSI A, B, C get involved on this VNI segment, 5000 segment. Now that's the TEP table. So the second one is a MAC table. MAC table is a very important one when it comes to layer 2 switching. So the same thing happens when the new VM comes in, and they just ESSI host or hypervisor, I should say. Hypervisor just capture just is able to see all the MAC address. See this VM's MAC address, which is the MAC address 1. So they just build a table for MAC address A is mapped to the map this TEP IP and also have a VNI ID. So that's a MAC table. MAC table is a mapping of VM MAC address to the TEP IP. So that means they should know the location of the VM, or should know the location of this Mac 1. Yeah. So the same thing happened. They just collected, just send out to the centralized controller plane, which is CCP. CCP just help collect all of them and hand out all the information to the to every transport node to make it common or the same scenario shown in, at the every transport node. So that means that ESS, for example, ESS-A can see this table, Mac2, where's the where Mac2 is, where the Mac3 is, where Mac Mac1 is, and is associated the TPIPs. Okay, op table. Op table means when you look at the op protocol, op table just a association between a MAC address and IP. Op table is kind of association of the IP and the MAC. So someone just wanted to send out a layer 2 frame. She just asked, I just know the destination or destination IP. But it doesn't know the MAC address of this IP, so they have to do a app resolution, which is broadcast to ask which one is IP, blah 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 blah. Please tell me your corresponding MAC address. Then later on, I'll use this MAC destination MAC as a layer 2 frame as a part of encapsulation of the layer 2 frame. So to form the whole Ethernet frame. So that's the app. That's pretty simple theory of the how app works. So here, for every VM, we just NSX just automatically automatically collects MAC address 1 and this IP. There's an association or there's a mapping from between MAC and IP. So here we have the app table. Because NSX just just working in the hypervisor or at the hypervisor or at the kernel part, so they can see anything about the packet, about the MAC, about VM IP, VNI numbers, so all of the things they just can capture. So the same thing happens when this those information or records get collected and also sent to the CCP to do the aggregation, and the CCP or control plane will just hand out or distribute all of the records, the same records, to every transport node, so that every transport node just know to see the whole same scenario of the whole system. So that's our table. And so just give you a scenario. For example, this end-to-end communication. If there's a VM1 and a VM2, how they transfer their packet in between. For example, VM1 as a source virtual machine, and he wanted to send out the packet to IP 10.1 to this one 10.12 at their destination. And then VM1 and VM2 are located or sitting in the same segment, which is web segment, and the VNI ID is 69632. So let's see how it works. So it's a packet sent out from the VM, and here is a transport node A. Transport node A has a VTAB IP. Oh, sorry about that. Just and because they are using the overlay segment, so they have to leverage the underlay physical network or physical routing or switching to transmit the whole, or to traverse the whole packet on the web logical web segment. So here, because transport node has the 3 tables, they just thought that the destination 10, 10, 1, 10, 12 is sitting on the transport node B, whose VTAB IP as this one 1152. So in order to transfer the whole packet to the destination, they have to do the encapsulation, the Geneve encapsulation. So that means they have to create a Geneve tunnel encapsulation. So for this IP, so source IP, Geneve's, when we look at the Geneve encapsulation, is Geneve's source IP is a VTAB IP-A, and destination IP is a VTAB transport node B, which is 1152. So source IP 1151, destination IP is 1152. So that's the Geneve tunnel header. And original packet that the VS virtual machine 1 sent out is the same, but get embedded into the whole Geneve encapsulations. So that's the how VM1 communicate with VM2 work. So let's talk about the broadcast and the BOM. So just BOM means B means broadcast, U means annual unicast, and M means multicast. The broadcast and multicast, how NSX deal with BOM traffic, because in the previous slides we talk about unicast to unicast communication, which VM1, how VM1 talk to VM2, which is unicast communication. So we for unicast communication, NSX just counting on some of the tables, for example, those 3 tables to just transmit the whole packet, and also give you a appropriate Geneve tunnel encapsulation, and also send the whole Geneve encapsulation to the destination, which is TMB. This is a TMA. So here we are talking about broadcast and unicast and multicast, unknown unicast and broadcast. So that means, for example, this website, this virtual machine, web1, is located on the host host 1. Sometimes web1 just sending out a broadcast from, for example, for some reason, you have to send out some of the broadcasts from upper layers requests. So for broadcast means for the whole segment, which is a green segment, we have to ensure that every virtual machine on this same segment will get this broadcast packet or frame. That means here, for example, let's say in this case, we have a TP4, host 4, host 5, host 6, 7, 8, 9, and 1, 2, 3. We have 9 hosts that are participating in the segment grain. Let's say that, imagine that, or just there's a segment grain. So there are 9 hosts which join this segment grain segment. So at the point in time, web1 just send out a broadcast. So how this broadcast will travel to every host, and in turn travel to the all VM, which are setting on the segment green. So those VM all are setting on the green segment. So here we have 2 methods to implement this. One is what we call is head-end replication. That means that from the source side, which is web1, is located. Host 1 is responsible for copy all of the, or duplicate all of the broadcasts to, for example, from 1 copy to 9 copies, because there are 9 hosts right here, or 9 TNs right here. They have to ensure that this broadcast packet should travel to every host. So they have to copy 9 times to form 9 copies. So that's the responsibility of the source side, which is the host 1. Host 1 just send out every packet to host, to every host respectively. That's the method, one method. So head and replication. Head and replicate. So head and will replicate this broadcast, this multicast or unknown unicast to the appropriate copies and send out to every host or every TN. Alternative or the second method of this transformation is or transmitting or just what we call as hierarchy replication, 2 tiers. 2 tier means we have 2 tiers. That means that if we look at this physical topology, we have a physical router here. We have physical router here, right? And then we have 3 subnet. Subnet A, subnet B, subnet C, right? So that means that we have 3 different subnets. So to facilitate the whole replication process, we can use the 2-tier replication method. That means that, for example, at the point in time, the web 1 just send out a broadcast, and for host 1, they just know, host 1 just know, oh, okay, we have enough tables to see the whole NSX system. We know that there are 9 hosts that are sitting on 3 subnets, which are subnet ABC. So host 1 is sitting on the subnet A, right? So for the first tier, for the beginning of the replication, they just copy or replicate the packet to host 2 and host 3, which are sitting on the same subnet, which is subnet A, right? And also replicate 1 copy to the subnet B, 1 copy to the subnet C, and just randomly send out to host 7 or randomly send out to host 4. That's it. That's the first tier replication. Then for the second tier replication is because host 4 just got the latest packet, and host 4 has the ability to copy it again to host 5, and for example, host 7 is make a copy to the host 8 and host 9. This is a 2-tier. So it means source, which is a host 1, make first tier replication to specific destinations, and the specific destinations do the second tier replication for their local distribution. That's the 2-tier replication for the broadcast and multicast, or for the BUM traffic handling. That's the whole process. That means for the most optimized one is this kind of 2-tier hierarchical replication. Yeah, TPT3, and also to randomly pick host 4 and host 7 and send out 1 packet each. And then for the local area, just the whole 7 doing the replication, second tier replication to for the TEP9 and TEP8. So that's a 2-tier hierarchy replications. So keyword, very, very simple and very short video today. I just emphasize VNI, Geneve. Some of the questions were related to the encapsulation and also talk about BAM, traffic handling, and also 3 tables you have to remember, which are very, 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 very critical for NSX switching. So that's it for today's lesson. I hope you enjoy it, and I'll see you in the next lesson.